Hi, good morning. I'm happy to be here this morning and chat with you guys. Like Chelsea said, I'm Corey. And I'll be talking about our early detection initiative at the Vanderbilt Memory and Alzheimer's Center and some of the work we've been doing in that space. Hopefully you find it useful, and I'm happy to take any questions at the end as well. I have no disclosures. Here's a quick overview. So first I'll give some information on our center, some of our longitudinal cohort studies, and give more context about the type of work that we're doing. Then I'll really hone in and focus on the early detection initiative, and specifically these themes outlined here, which is where a lot of my own research focuses. Oh, is this better? You hear me better now? Sorry. Is that better? No. Maybe I could stand closer. So we're all right. Is that okay? Nothing? Sorry. All right, I'll just lean into it. How about that? All right, so VMAC, or the Vanderbilt Memory and Alzheimer's Center, is a trans-institutional center. We're housed at the Vanderbilt University Medical Center, but we also have faculty members at Vanderbilt University on the university side, as well as Meharry Medical College. Our mission is to enhance knowledge to solve the complexities underlying the pathophysiology, early identification, and treatment of ADRD. We are really a truly interdisciplinary group. Amongst our 61 faculty members, we represent 21 different departments on campus, and we're comprised of neurologists, neuropsychologists, epidemiologists, cardiologists, engineers, and many more specialties as well. I think that's a real strength of our center, is that we can kind of collaboratively build on each other's knowledge. It's a unique setting. It's one that I haven't been in before, and it's been really great to do research in that kind of setting. So our signature cohort study is called the Vanderbilt Memory and Aging Project, or VMAP. This was launched in 2012, and it's a longitudinal observational cohort study, meaning that we bring in a cohort of individuals and we follow them for a long period of time to see what factors might influence the future development of memory loss. We recruited adults at baseline who were over the age of 60 and who did not have dementia, clinical stroke, or heart disease. And we really sought out to enrich that cohort for MCI, or mild cognitive impairment, to ensure that we're going to capture some people who do go on to develop Alzheimer's disease in the future. So one of the main goals of this study is to assess cardiovascular and cerebrovascular correlates of cognition and brain health and aging. So we're interested in that heart-brain connection, specifically how changes in cardiovascular functioning earlier in life influence later brain aging. And we've been following these patients for 9 years now. So we're completing our 9-year data collection at this time, and we've been assessing them every 18 to 24 months over that period. So we have a really rich database built up from this study. So given the success of the initial study, we received funding to expand that study to now include 1,000 participants. So we are recruiting to kind of build up that cohort to 1,000. Some of the initial findings from the original legacy cohort, we call it, were that, like I said, cardiovascular health is important, but it's really important earlier than any observable cognitive changes are present. So we know that cardiovascular health in midlife is kind of where the point of intervention is if we want to prevent memory loss in late life. So we dropped the age band down to 50, and we're only recruiting participants who have no cognitive impairment. So no patients with MCI will be included in this expansion cohort. And recruitment's ongoing. We've got about 500 or so total as of now. We started recruiting last year. So we collect a lot of data for VMAP, and here are some of the broad categories that we look at. I'll go through and touch on each of these in a little bit more detail. Sorry, I'm trying to find my mouse on here to scroll through my notes. All right. So as for demographic information, we of course get age, sex, education, race, ethnicity. These are kind of some of the things that we covary for in all of our analyses to see if we can kind of control for that so that we can really isolate the types of problems that we're interested in intervening for. We collect some clinical information like height, weight, blood pressure, health history. We really have a particular focus here on cardiovascular risk factors, so we get a really thorough smoking history and things like that. We do some clinical blood work. These results are released to the patient and their doctors if they wish. This includes basic clinical labs like cholesterol, blood sugar, thyroid levels. We also have some markers of inflammation, things like that. We have a whole team of geneticists at our center, and they do a lot of really cool work on the genetic side. I don't understand much of it, so I can't comment on too much of that, but they're doing some really cool work with sex differences in Alzheimer's disease and also in resilience to Alzheimer's disease. So patients who have Alzheimer's disease-like changes in their brain, but they don't actually develop symptoms. They want to know what's the genetic architecture of that. We do really comprehensive cognitive testing. So every participant who comes through gets a full neuropsychological assessment. We look at domains like memory and executive functioning and language abilities, among other things. We also do a clinical dementia rating interview, or CDR, with each participant and their study partner. And we also have a whole host of questionnaires that we give to participants and their study partners as well. Our actigraphy data is interesting. It's using an Actigraph device, which is like a Fitbit. It's a wristwatch kind of device that you wear. We send it home with participants for 10 days, and it measures their activity levels and sleep cycles during that 10-day period. And it gives us some really great information as to their physical activity, how well they're sleeping at night, those kind of things. We also have an ambulatory blood pressure monitor that we send home with participants, and they wear this for 24 hours. It takes regular blood pressure readings throughout the day, and it gives us an idea of the variability in their blood pressure throughout the day, which we found to be an interesting variable for brain aging. For cardiac imaging, we do a cardiac MR and an echocardiogram, and that allows us to calculate some cool variables like pulse wave velocity, which is kind of our measure for aortic stiffening, and some other cool things there. We do a pretty comprehensive neuroimaging protocol using our 3T brain MRI. We do both structural and functional imaging. And finally, we are looking at a lot of different molecular biomarkers, both some that are well established, like kind of the core Alzheimer's disease biomarkers in the spinal fluid, but also more exploratory, things like new and exciting blood-based biomarkers, which I'll talk more about in a bit. All of our fluid biomarkers are sent to the University of Gothenburg in Sweden, and the team there, which is really the worldwide experts on fluid biomarkers in Alzheimer's disease, they're always sending us new data with new analyses that they're running for novel biomarkers. It's really kind of an exciting collaboration there. So in 2020, we received funding from the National Institute on Aging to establish an exploratory Alzheimer's disease research center at Vanderbilt. This is one of 33 such centers in the country, and it's the first one in Tennessee. Part of this is our clinical core, which is led by Dr. Paul Newhouse and Dr. Katie Gifford. And one of the main initiatives of the clinical core is to establish a new cohort, the Tennessee Alzheimer's Project, or TAP. So this is similar to what I just outlined with VMAP, the other cohort study, but the restrictions are a bit broader as far as where they can fall on the cognitive spectrum. So we're recruiting participants with normal cognition, with MCI, and with mild dementia for this cohort. So as a center, we have put forth these 4 key research initiatives, and for the rest of the talk today, I really want to focus in on the early detection initiative. So what do we mean when we talk about early detection? You can see here a graph of changes in cognitive functioning with aging. The solid line represents normal aging, and the dotted line represents the path of Alzheimer's disease. AD pathology accumulates over decades and can be detected prior to any observable cognitive changes. We refer to this stage as the preclinical stage of AD, and it's composed of participants who have AD pathology but are completely asymptomatic, and those who are only mildly symptomatic or in the early symptomatic stage before we would call them MCI. So this is the group of people in this preclinical stage that we're looking to target with our early detection efforts. So why is it important to identify those individuals with preclinical AD as early as possible? First, it gives us an opportunity to talk with patients about other problems like sleep apnea. I feel like that got louder, right? All right, great, sorry. I moved to Tennessee 2 years ago from Chicago and really discovered that I have significant seasonal allergies. So my nose is a bit runny and it's a little bit hard to project today. So thank you guys for bearing with me, and thank you for turning up the mic. So why is it important? It gives patients an opportunity to consider other causes of memory loss, things like sleep apnea, cardiovascular disease, depression, these other factors that are treatable and can actually influence the course of the disease or the manifestation of symptoms in a disease. So it gives them an opportunity to work on some of those modifiable risk factors. It also creates an opportunity to initiate treatment prior to significant neuronal loss. So there's a new FDA-approved Alzheimer's drug I'm sure you guys have heard of, aducanumab. It's a bit controversial, but I think it's pretty clear that if it's going to work, it has to be administered very early on before there's significant neuronal loss. So being able to identify those patients with pathology before they start to have symptoms is really critical for starting early treatments. We also know that lifestyle interventions like diet and exercise are critical for slowing the progression of Alzheimer's disease and reducing the manifestation of symptoms. So identifying early changes that are probably associated with Alzheimer's disease really allows patients to take advantage of some of those preventative strategies at a really critical point in the disease. It also increases safety. It allows for consideration of safeguards. If someone knows that they're going to go on to develop memory loss, they're able to put in some safeguards with their family to make sure that they're going to be safe with skills like driving and remembering to take their medications, things like that. It also allows individuals to make important decisions while they still have cognitive capacity. If you wait too long, it's hard to make decisions with regard to complex matters like finances and medical decision making. So being able to make your wishes known at a time when you have the cognitive capacity to do so really requires early detection. And if you're able to put those safeguards in place and plan for the future, that's going to delay placement into nursing homes, long-term care facilities, and of course it's going to reduce healthcare costs, both for the patient as well as overall for the Medicare system. So if you don't believe me about the reducing costs of Medicare, I think this slide outlines how essential that point is to CMS, or the Centers for Medicare and Medicaid Services. In 2011, they altered their annual wellness visit policy to include detection of cognitive impairment for all older adults. On the right, you can see a flow chart of how that occurs. So first, a risk assessment is performed, and if there are signs of cognitive impairment, a brief assessment is performed. This can be something like a MoCA, cognitive screening measure, something like that. If it's abnormal, the patient would then be referred for a full dementia workup. So our efforts in the early detection initiative are really targeting these kind of earlier steps, the risk assessment, the brief cognitive assessment. We're trying to improve the accuracy of being able to detect early changes that are concerning for Alzheimer's disease so that we can intervene at an earlier time. So now I'll talk about some of the current or recent research from our group within the Early Detection Initiative. And first, I'll talk about the concept of subjective cognitive decline. So subjective cognitive decline, or SCD, refers to an individual or their loved one's subjective reporting of cognitive changes. The graph you see here is similar to the one I showed earlier, where you can see declines in cognitive performance over time associated with Alzheimer's disease. So SCD comes into play during those preclinical stages before MCI. And measurements of SCD have been shown to be a promising marker for early cognitive changes. So we really have devoted a lot of time and efforts at refining this process of assessing SCD. So research from Dr. Gifford in our group has shown that individuals with SCD are actually twice as likely to be diagnosed with MCI or dementia over a 3-year follow-up period compared to those with minimal complaints or no complaints. But one important question to ask is what causes SCD, or what causes someone to report these changes that they've noticed in daily life? This study from our group, led by Dr. Gustafsson, examined that question exactly. And he looked at over 1,000 participants who completed a measure of SCD, as well as an objective neuropsychological assessment. And there was some modest association between SCD and cognitive performance in the domains of memory and executive functioning. However, the associations with SCD were much stronger for things like depression and anxiety. So it's not just observable cognitive changes that are causing SCD, but also mood factors as well, which kind of complicates the picture a little bit if you're trying to use them to detect Alzheimer's disease. So we wanted to ask the question, is SCD associated with AD pathology? So this study, led by Dr. Gifford again, examined associations between SCD, both self and informant reported SCD, so an individual's own perception of how they're doing, as well as their loved one's perception of how they're doing. She looked at over 2,000 individuals in this study and divided participants up into 4 different groups based on their SCD status. So one group was made up of those with no complaints, so neither the patient nor the informant had any complaints about their cognition. The second group was made up of those who only the participant themselves had complaints. The third group is informant-only complaints. And then finally, the mutual complaint group is where both the informant and the participant themselves had complaints about their memory. And she found that only mutual complaint was associated with AD pathology at autopsy, so the presence of plaques and tangles. Only mutual complaint, not self or informant only, but whenever both the participant and their loved one are both mutually reporting changes, we see AD pathology at autopsy. So based on those results, we know that AD can be associated with postmortem neuropathology. So the next thing we sought out to do was understand if SCD is associated with in vivo biomarkers of AD, things that we can measure while the participant is still alive. So this study used data from VMAP, and we utilized an SCD scale that we actually created in-house and kind of used advanced psychometric methods to take the good questions from other measures and put them together into one that we think is the most useful. So in addition to examining if SCD is related to CSF biomarkers, we also wanted to know if that association changes depending on these demographic factors like sex, reading level, and education. We know from past research that these factors can influence how an individual reports symptoms. So we wanted to see how that would modify our associations. So as you can see illustrated on the left, we found that SCD was associated with CSF markers of amyloid pathology. It was not associated with other AD biomarkers like tau, But amyloid, which is thought to be one of the earliest changes associated with Alzheimer's disease, was associated with our SCD measure. And we also found that this association differed depending on the participant's sex and education level. So on the top figure on the right, you can see illustrated that the association between SCD and CSF amyloid levels is quite strong in men, as evidenced by the black line there. And then likewise on the bottom right, you can see that associations are stronger in those with higher educational levels. These results are a bit perplexing to us. The sex differences are actually contrary to past work, which shows that when women report SCD, they're more likely to decline in the future. We're still trying to understand better why exactly these differences are here, but one hypothesis is that older women are actually more likely to have more medical comorbidities than older men. And same is true for those of lower educational levels. They're more likely to have more medical comorbidities. So we think that there might be more alternative causes of their report of decline that are not specifically just due to Alzheimer's disease. We want to understand that association a little bit better, but we're not quite there yet. So here's another study that we conducted that was trying to answer the question of whether SCD is associated with in vivo biomarkers of AD. Here we examined associations between a blood-based biomarker for Alzheimer's disease, plasma p-tau 181, which I'll talk more about later, and its relation to self and informant reported SCD in a large cohort of over 1,000 individuals. We also want to know which clinical or demographic factors may influence this association. What we found is that plasma p-tau 181 levels were associated with informant-reported SCD, as you can see on the left, and more so for participants with MCI or dementia, as you can see in the red and blue. We also found similar sex differences with regard to self-reported SCD, as you can see on the right, where men having higher levels of plasma p-tau 181 had greater report of symptoms than women. So putting that all together, we found that SCD is associated with AD, but this association can depend on several factors. It's more likely that SCD is related to underlying Alzheimer's pathology when there is no significant mood symptoms, when the patient and their loved one are both reporting changes, and when the patient is more highly educated and male. And again, we think that's probably related to having fewer medical comorbidities. So in the future, we hope to examine those sex differences a bit more, tease apart what exactly is driving that, and understand if our hypothesis is correct, that it is medical comorbidities driving that, or if not, what else could be playing into that. We also hope to take measures, of SCD and integrate them with other accessible biomarkers, things that can be administered in a primary care visit very easily to increase the accuracy. And I'll talk more about that, some of our work along those lines a bit later. But first I want to talk about some of the work with blood-based biomarkers. So I've mentioned one already that we've utilized, but I'll spend some more time specifically talking about these blood-based biomarkers because they're new and they're actually really great tools for early identification, or they can be. So as you know, Alzheimer's disease is made up of aggregation of two abnormal proteins, amyloid and tau. And for a very long time, these proteins were only known by their end result that you could see at autopsy, which is plaques and tangles. But by the 90s, it became possible to detect these proteins in the spinal fluid. So from then up until the 2000s, that was the primary way of understanding if someone had biological Alzheimer's disease during life. In the 2000s, PET radio tracers were developed for each of these proteins so that now we can do a PET scan and see spatially, not just a value, but where it's located within the brain, the distribution of these two proteins. So CSF analysis and PET imaging have led to countless breakthroughs in the field of Alzheimer's disease research, but they're not super useful clinically. They're expensive, they're inaccessible, they're a bit invasive. No one wants to get a lumbar puncture. I've had to consent a lot of participants for lumbar puncture in my days, and I can promise you everyone is scared of it. And PET imaging, people get freaked out by the radiation. So it's not something that can be widely implemented, especially not in primary care clinics. So recent technological advances have allowed us to detect those same proteins in the blood, which is really a game changer. It allows for very easy collection of the sample that we need, and it turns out to be quite accurate. So one such blood-based biomarker is plasma levels of the tau protein. I'll say there's a lot of different varieties of tau. Tau is a protein that's involved in microtubules within the neuron that provide structure and help with signaling. But not every type of tau is specific to Alzheimer's disease. This blood test is measuring all types, so it's really a marker of neurodegeneration. So when neurons die, they release all the intracellular components into the spinal fluid, which eventually makes its way to the blood. So this marker can be thought of as kind of a non-specific measure of just neurons dying in the brain. So one basic question we wanted to ask is if these plasma total tau levels predict changes in cognition. So we used data from VMAP, and we took their baseline plasma total tau levels from their study entry point, and then we looked at their cognition over the follow-up period, which I mentioned it was about 7 years during this study. And we did find that it was associated with cognition in one domain, and that's processing speed. So it was not associated with cognition in other areas like memory or executive functions, things that might be more specific to Alzheimer's disease, but it was associated with this kind of non-specific marker of processing speed, which is kind of interesting. Processing speed is the most consistent cognitive change associated with normal aging. As we get older, we slow down a bit. So this finding is just really kind of hammers down the point that this marker is very non-specific. And we saw that associations were stronger in individuals with MCI. They probably just had more variance in their test scores to show that decline. You can see that in the red bar there. So a non-specific biomarker for neurodegeneration can be helpful in some situations, but we're really interested in detecting early Alzheimer's disease-related changes. So we really hope to have something that's more specific to that condition. We know that in Alzheimer's disease, the tau protein becomes hyperphosphorylated. So a biomarker that detects tau in this hyperphosphorylated state would be more specific to Alzheimer's disease and therefore more useful to us. So plasma p-tau 181, which I mentioned before, is really just that. It's a blood-based biomarker that's very specific to Alzheimer's disease. There's been a lot of research that shows that if you take participants with Alzheimer's disease, healthy controls, and participants with dementia due to another cause like frontotemporal dementia, it actually really successfully distinguishes between those conditions. It's very specific to Alzheimer's disease changes. So we wanted to ask the same question of this biomarker, that is it associated with cognitive impairment? So in our study, we looked at over 1,000 participants from the ADNI database, which is a large multi-site observational study. And we found that plasma p-tau 181 is associated with tests of memory, executive functions, and language, areas that are more commonly affected by Alzheimer's disease. We also found that these associations are stronger in individuals with MCI or dementia, as you can see here in the red and blue lines. So to summarize our work with blood-based biomarkers so far, we've examined 2 different markers of the protein tau, one measuring total levels of all types of tau protein, and there we found that it is associated with longitudinal slowing of processing speed. The other marker is more specific for Alzheimer's disease type of tau, and we found that this marker was more associated with cognitive changes that we would expect in Alzheimer's disease. So we want to continue these lines of research and expand it beyond just looking at cognition, but looking at things like brain structure, if the brain is shrinking or atrophying in certain areas associated with these biomarkers. Also, we want to look at functional abilities, kind of the real world take home for patients. Is their functioning going to decline if they have an elevated score on this test? Really, the efforts that we're doing here are meant to provide more context for providers who are delivering these results to patients. These are not available clinically yet, but they will be in the near future. And we want to know for sure exactly what an elevated test score means. We also want to understand which clinical or demographic variables modify those associations. So there's already been some great work that people with liver disease, actually, this is not the best biomarker for them because we're measuring it in blood. If you're having difficulties with your liver processing blood, it actually alters the values of this biomarker. So we want to understand which factors like that influence the results and the test's ability to predict meaningful outcomes. So the next focus in our early detection initiative has been on predicting risk of dementia and really quantifying that risk as well. So through our own research and that of the broader ADRD research community, we know that measures of SCD, blood-based biomarkers, ApoE genotype. ApoE is the strongest genetic factor for Alzheimer's disease outside of the familial variants. And also cognitive screening measures like the MMSE or the MoCA. We know that these are useful tools for predicting dementia risk, but we want to take it a step further and start to integrate them to determine what's the best set of tests that you can give to most accurately and efficiently predict risk of dementia. So in this study, we wanted to ask the question of which accessible measures add value beyond just demographic factors and cognitive screening alone, which a lot of providers are already kind of basing their estimates on those kind of values. So we used data from VMAP, and we looked at multiple different predictors to determine which is the most successful in predicting conversion to dementia, as well as amyloid status, as determined by CSF analysis. So some of the predictors we used are ApoE status. We define this as positive or negative for the E4 risk allele. If they had one E4 or two E4s, they were positive. If they didn't have any E4 alleles, they were negative. We also looked at two blood-based biomarkers. These are both kind of non-specific markers for neurodegeneration. Plasma total tau, which I talked about, as well as plasma neurofilament light, which is a similar biomarker. We also looked at self and informant-reported SCD on the ECOG, which is a widely used measure of SCD. And then we looked at self-reported SCD on our own Vanderbilt SCD scale that we developed in-house. We found that ApoE was the most robust predictor, so that genetic, we've known for a long time that ApoE is important for Alzheimer's risk, and we kind of confirmed that here, that knowing ApoE status gives us the most information about who's going to develop dementia in the future. We found that the plasma or the blood-based biomarkers added value only when we were looking at participants with MCI. They weren't as useful in cognitively normal participants. As for the measures of SCD, we found that they did add value, but in different ways. So self-reported SCD was useful in cognitively unimpaired participants. These are ROC curve graphs, and on the left, you can see the green line, which represents self-reported SCD on our own Vanderbilt SCD scale. It overlaps significantly with the red line, which is ApoE status. So its ability to predict amyloid status in this case is similar to that of ApoE. On the right, we can see that informant-reported SED, the blue line was more useful. It wasn't quite on par with ApoE status, but it certainly outperformed self-reported once they reached the mild cognitive impairment stage. This is due to anosognosia, a lack of awareness of deficits that very commonly is accompanied by Alzheimer's disease. So we hope to continue this line of research to investigate different combinations of predictor variables and really hone in on the best method of accurately and efficiently predicting risk of dementia in the clinic. One big step towards this will be replacing those non-specific plasma biomarkers with the more specific plasma p-tau 181 biomarker. And then once we have developed an effective risk prediction model, we hope to validate that in external cohorts, specifically in cohorts that with more ethnic or racial diversity than our own. So obtaining an accurate estimate of an individual's risk for developing dementia is really just the first step. As I mentioned before, there's lots of benefits for early identification specific to the patient and their families. So now I want to talk about our efforts towards actually disclosing risk estimates for dementia to patients and their loved ones. So there's been a number of surveys in the broader literature, and they've all found one thing in regards to this topic, and that's that patients want to know their risk status. They want to know if they're at increased risk of developing dementia. The study outlined here on the bottom shows that patients are actually more likely to take steps towards disease prevention, to make positive health behavior changes whenever they're informed that they're at increased risk. So this is the newly FDA-approved medication, Aduhelm, or aducanumab. And with the FDA approval of this anti-amyloid therapy, it's really cleared the way for other similar drugs to be approved, and there's a lot of others coming down the pike. These drugs require administration very early in the disease process, and they require biomarker evidence of amyloid pathology. So because of this, the field is really moving towards requiring patients to know their risk status if they want to receive treatment. So because of the inevitability of risk disclosure in AD, we pose the question of how do we disclose these complex test results to patients with cognitive impairment in a safe and comprehensible way. So we're currently recruiting for a study to develop educational materials to aid in this process. We're working with our Center for Effective Health Communication, which they have been really excellent just with increasing the readability and the visual layout of our materials so that they're very easily comprehensible even to participants who have some degree of cognitive impairment. Once we finalize our draft, we're going to run it through some focus groups of individuals with MCI to see what they think of it. That'll be happening next month and into September as well. So once these educational materials are finalized, we want to put them to use in a randomized trial. So we'll be conducting a trial where we actually disclose to a participant with MCI their 4-year risk estimate of converting to dementia. These estimates will be developed or will be created by these models where we consider age, sex, education, MMSE score, and then the results on the plasma p-tau 181 test. These models were developed by our collaborators in Sweden, and they've actually published a web tool at predictprogression.com where you can go on and enter all the different variables there and get a risk estimate. This is just for research purposes only, but I found it kind of fun to go on there and see the relative weight of different things like the MMSE. So for the trial, some of the outcomes we're looking at include psychological response. So we'll be looking at anxiety, depression, hopelessness, and event-related distress, kind of a marker of almost PTSD. And then we'll be looking at that immediately following the disclosure and then again at 6 months afterwards. We're also interested in comprehension, so assessing the ability of the patient to teach back their results to us in an accurate way. We'll look at that again immediately following the disclosure and again at 6 months. So some other directions we hope to explore in this space include looking at the effects of risk disclosure on participation in research. So we think that if people are informed of their chance of developing dementia in the future, they might be more likely to participate in research, and particularly in clinical trials where we so desperately need research participants. We also want to see how risk disclosure varies in diverse patient populations. So unfortunately, the vast majority of the work in risk disclosure has been done in white populations and well-educated populations. We want to see if the results that they found ring true in other more diverse patient populations that really represent the communities that are affected by this condition. And last, we want to see if telling someone their risk status increases these health behaviors, does it actually change the course of their disease? So if someone is told that they're at increased risk and they start exercising, they start eating a healthy diet, they start being cognitively active, maybe taking a medication, does that actually change their propensity to developing Alzheimer's disease? So the last thing I'll mention is our data sharing portal, which can be found at vmacdata.org. Here you can find summaries of all of our data from VMAP, and we'll be adding data from TAP there as well in the future. There's some cool data explorer options where you can see how things change over each epoch of our study. You can get breakdowns specific to specific demographic groups. There's a lot of really cool tools that they've integrated there. And it's freely available to the public. So if you have a research question that you want to ask, and our data can be of use, we want to share it. So if there's any interest in that, I'm happy to talk about that afterwards, or you can email me. Finally, I'll just say a big thank you to all of our research participants, our team at the Vanderbilt Memory and Alzheimer Center, some of whom are listed there, our collaborators and our funding sources,